Sklearn Manifold. Description: Manifold learning is a set of techniques used to learn the underlying structure of high-dimensional data by representing it in a lower-dimensional space. The goal is to preserve the essential relationships between data points while reducing dimensionality, making it easier to visualize and analyze the data. This often involves finding a lower-dimensional representation of the data that preserves certain properties, such as local neighborhoods, distances, or global connectivity. Inputs. Input 1 data, a dataset represented as a 2D array, where each row represents a data point and each column represents a feature. Input 2 parameters, various parameters that control the behavior of the manifold learning algorithm, such as the number of neighbors, embedding dimensions, and regularization strength. Outputs. Output 1 reduced dimensionality data, a 2D array where each row represents a data point and each column represents a feature in the lower dimensional space. Output 2 reconstruction error, a measure of how well the original data can be reconstructed from the lower dimensional representation. Steps. Step 1: Initialization. The manifold learning algorithm starts by initializing the embedding space and assigning initial positions to the data points. Step 2: Optimization. The algorithm iteratively adjusts the positions of the data points in the embedding space based on the chosen distance metric and constraints. This process aims to minimize the distortion introduced by reducing the dimensionality. Step 3: Embedding. Once the optimization process converges, the data points are embedded in the lower dimensional space, providing a representation of the original data that preserves the desired properties. Metrics. Metric 1: Reconstruction error measures how well the original data can be reconstructed from a lower dimensional representation. Metric 2: Local neighborhood preservation measures how well the local neighborhood structure of the original data is preserved in the lower dimensional embedding. Metric 3: Global connectivity preservation measures how well the global connectivity structure of the original data is preserved in the lower dimensional embedding. Visualization plots. Visualization plot 1: Scatter plot. This plot visualizes the data points in the lower dimensional embedding space. Visualization plot 2: Manifold structure plot. This plot shows the underlying manifold structure that the algorithm has learned. This is typically represented as a smooth surface in the embedding space. Fine-tune parameters. Parameter 1: N neighbors. The number of neighbors to consider for each data point when constructing the local neighborhood graph. Parameter 2: N components. The dimensionality of the embedding space. Parameter 3: Metric. The distance metric used to compute the distances between data points. Parameter 4: Regularization strength. This parameter controls the trade-off between preserving the local neighborhood structure and reducing the overall embedding error. Uncertainty methods. Uncertainty method 1: Confidence intervals. By sampling the embedding space multiple times, we can calculate confidence intervals for the location of each data point in the embedding space. Uncertainty method 2: Bootstrap aggregating. By sampling the original data with replacement, we can create multiple different embeddings and calculate confidence intervals for the location of each data point. Challenges and fixes. Challenge 1: High dimensionality. When the original data is highly dimensional, the manifold learning algorithm may struggle to find a suitable lower dimensional representation. Sample use case that resulted in challenge 1: A dataset with thousands of features. Fixes to challenge 1. Feature selection. Select a subset of relevant features to reduce the dimensionality before applying the manifold learning algorithm. Principal Component Analysis (PCA). Apply PCA to reduce the dimensionality of the data before applying manifold learning. Challenge 2. Nonlinearity. When the data exhibits strong nonlinear relationships, the manifold learning algorithm may fail to capture the underlying manifold structure. Sample use case that resulted in challenge 2. A dataset with complex nonlinear relationships between features. Fixes to challenge 2. Choose a more powerful manifold learning algorithm. Explore algorithms designed to handle nonlinear relationships, such as ISOMAP, locally linear embedding (LLE), or T-SNE. Kernel methods. Employ kernel methods to map the data to a higher dimensional space where the relationships become linear, and then apply manifold learning in this space. Challenge 3. Outliers. Outliers in the data can significantly impact the results of manifold learning, leading to distortions in the embedding space. Sample use case that resulted in challenge 3. A dataset containing a few data points that are significantly different from the rest. Fixes to challenge 3. Outlier removal. Identify and remove outliers from the dataset before applying the manifold learning algorithm. Robust manifold learning algorithms use algorithms that are robust to outliers, such as robust locally linear embedding (RLLE) or ISOMAP with outlier rejection. sklearn, manifold, ISOMAP. Description: ISOMAP isometric mapping is a nonlinear dimensionality reduction technique that aims to preserve the geodesic distances between data points in a lower dimensional embedding. It is particularly useful for visualizing high-dimensional data that has a nonlinear manifold structure, such as images or text. Inputs: X. The input data, typically a NumPy array of shape n samples. N features, where n samples is the number of data points and n features is the number of features. N neighbors, the number of nearest neighbors to consider when constructing the neighborhood graph. This parameter affects the smoothness of the embedding and the computational complexity. Outputs: embedding, the resulting low-dimensional embedding of the data. A NumPy array of shape n samples. N components, where n components is the desired dimensionality of the embedding. Reconstruction error, the reconstruction error of the embedding, which measures the difference between the original distances in the high-dimensional space and the distances in the low-dimensional embedding. Steps: 1. Construct a neighborhood graph. The algorithm first constructs a graph where each data point is connected to its k nearest neighbors based on the Euclidean distance. 2. Compute shortest paths using the constructed graph. ISOMAP computes the shortest paths between all pairs of data points. These shortest paths represent the geodesic distances on the manifold. 3. Perform multidimensional scaling (MDS). The computed geodesic distances are then used as input for classical multidimensional scaling (MDS), which finds the optimal low-dimensional embedding that preserves these distances as much as possible. Metrics: reconstruction error measures how well the low-dimensional embedding preserves the original distances in the high-dimensional space. Lower reconstruction error indicates a better embedding. Stress: a similar metric to reconstruction error, also known as Kruskal stress, which measures the discrepancy between the distances in the high-dimensional space and the distances in the low-dimensional embedding. Visualization plots: scatter plot. The low-dimensional embedding can be visualized using a scatter plot, where each point represents a data point and its position in the plot corresponds to its coordinates in the embedding. This plot helps to identify clusters and nonlinear structures in the data. Pairwise distance plot: a matrix plot that shows the pairwise distances between data points in the high-dimensional space and the low-dimensional embedding. This plot helps to visually assess how well the embedding preserves the distances. Fine-tune parameters. N neighbors, the number of nearest neighbors used to construct the neighborhood graph. A larger value can lead to a smoother embedding but might oversmooth nonlinear structures. N components, the desired dimensionality of the embedding. Lower dimensions can lead to a more compact representation but might lose important information. Metric, the distance metric used to compute the nearest neighbors. Different metrics can lead to different embeddings. Eigensolver, the solver used to compute the eigenvectors and eigenvalues in the MDS step. Uncertainty methods. Non-isomap does not directly provide uncertainty estimates for the embedding. Challenges and fixes. Challenge 1: high computational complexity. Computing the shortest paths between all pairs of points can be computationally expensive for large datasets, especially with a large number of neighbors. Sample use case that resulted in challenge 1: a dataset with millions of data points and a high number of neighbors, e.g. n neighbors 50. Fixes to challenge 1. Reduce the number of neighbors, n neighbors. This reduces the computational complexity of a shortest path calculation. Use a more efficient algorithm for shortest path computation. Consider using specialized graph algorithms, such as Dijkstra's algorithm or Floyd-Warshall algorithm, for more efficient shortest path computation. Challenge 2: sensitivity to noise. Isomap can be sensitive to noisy data, as noise can distort the geodesic distances and lead to inaccurate embeddings. Sample use case that resulted in challenge 2: a dataset with high levels of noise, where the original distances between points are heavily corrupted. Fixes to challenge 2: pre-process the data to remove noise. Apply noise reduction techniques, such as smoothing or filtering, to reduce the impact of noise. Use a robust distance metric. Consider using a distance metric that is less sensitive to outliers, such as the Manhattan distance or the Mahalanobis distance. Challenge 3: difficulty in handling data with complex manifold structures. Isomap might struggle to accurately embed data with highly complex or disconnected manifolds. Sample use case that resulted in challenge 3: a dataset with multiple disconnected manifolds or manifolds with multiple folds or loops. Fixes to challenge 3: consider alternative dimensionality reduction techniques. Explore other methods, such as T-SNE or UMAP, which might be better suited for handling complex manifold structures. Experiment with different parameter settings. Adjust parameters like n neighbors and the distance metric to find the best settings for the specific dataset. sklearn, manifold, locally linear embedding. Description: locally linear embedding (LLE) is a nonlinear dimensionality reduction technique that seeks to preserve local neighborhood relationships in the lower dimensional space. It assumes that each data point can be linearly reconstructed from its neighbors, and aims to find a low-dimensional representation that maintains these local relationships. Inputs. X. The input data, typically a 2D array of shape and samples. N. Features. Each row represents a data point in the high-dimensional space. N. Components, the desired number of dimensions in the lower dimensional embedding. This determines the dimensionality of the output. Outputs. Y. The reduced data, a 2D array of shape and samples. N. Components. Each row represents a data point in the lower dimensional space. Reconstruction error, the reconstruction error for each data point, which represents the deviation from the original data after projecting to the lower dimensional space. This can be used to evaluate the quality of the embedding. Steps. Neighborhood search. The algorithm first finds the k nearest neighbors for each data point in P. High-dimensional space. This defines the local neighborhood structure. Weight calculation based on the identified neighbors. Weights are calculated for each data point to represent the contribution of its neighbors in reconstructing itself. This is done using a linear reconstruction approach. Embedding optimization. The algorithm then finds a lower dimensional representation of the data that minimizes the reconstruction error while preserving the local neighborhood relationships as defined by the weights. This is typically done using an optimization algorithm, such as eigen decomposition. Metrics. Reconstruction error measures the average deviation of the original data from the reconstructed data in the lower dimensional space. A lower error indicates a better embedding. Neighborhood preservation measures how well the local neighborhood relationships are preserved in the lower dimensional space. This can be assessed using metrics like the preservation of distances between neighboring points. Visualization plots. Scatter plot. The reduced data can be visualized in a scatter plot to explore the relationships between data points in the lower dimensional space. Pair plot for lower dimensional embeddings, e.g., 2D or 3D. A pair plot can be used to visualize pairwise relationships between different components of a embedding. Fine-tune parameters. N neighbors. Number of neighbors to consider for each data point. This influences the local neighborhood structure and the resulting embedding. Method. The method used to solve the optimization problem for finding the embedding. Common options include standard eigenvalue decomposition and modified using the Hessian of the cost function. Eigensolver. The eigenvalue decomposition method used to find the embedding. Options include auto, dense, RPAC, and LOB-PCG. Uncertainty methods. Out-of-sample extension. While LLE is primarily designed for dimensionality reduction on training data, there are approaches for out-of-sample extension to project new data points to the learned embedding. This involves finding the nearest neighbors of the new point in the original high-dimensional space and using the learned weights to project it to the lower dimensional space. Confidence intervals. Estimating the uncertainty in the embedding can be done by analyzing the reconstruction error and its distribution. This can provide confidence intervals around the projected data points. Challenges and fixes. Challenge 1. High sensitivity to noise. LLE can be sensitive to noise in the input data, which can lead to inaccurate reconstruction and poor embeddings. Sample use case that resulted in challenge 1. A dataset with a high level of random noise might result in LLE misinterpreting noisy features is important for local neighborhood reconstruction, leading to a distorted embedding. Fixes to challenge 1. Preprocessing. Applying noise reduction techniques such as smoothing or filtering to the input data before applying LLE. Robust weighing. Using more robust methods for calculating weights that are less sensitive to outliers or noisy data points. Regularization. Adding regularization terms to the optimization problem to penalize large weights or high reconstruction errors, which can help mitigate the impact of noise. Challenge 2. Computational complexity. LLE can be computationally expensive, particularly for large datasets with high dimensionality. Sample use case that resulted in challenge 2. Analyzing a dataset with millions of data points and thousands of features might lead to long computation times for LLE. Fixes to challenge 2. Dimensionality reduction. Applying a preliminary dimensionality reduction step using techniques like PCA to reduce the number of features before applying LLE. Random subsampling. Using a random subsample of the data to train LLE, which can significantly reduce computation time while still providing a reasonable embedding. Approximate neighborhood search employing efficient approximate nearest neighbor search algorithms to speed up the neighborhood search step. Optimized solver choosing an efficient solver for the optimization problem, such as RPAC or LOB-PCG for larger datasets. sklearn Manifold MDS. Description: explain in detail. MDS stands for multidimensional scaling. It is a dimensionality reduction technique that aims to find a low-dimensional representation of data while preserving the distances between data points as much as possible. It is used to visualize high-dimensional data in a lower-dimensional space, often 2D or 3D, for better understanding and analysis. Inputs. Input 1. Explain in detail a distance matrix representing the pairwise distances between data points. It can be obtained from a variety of methods, such as Euclidean distances, Manhattan distances, or other similarity measures. Input 2. Explain in detail the number of dimensions n components to which the data should be reduced. This value typically depends on the desired visualization or analysis goals. Outputs. Output 1. Explain in detail an array of coordinates representing the low-dimensional embedding of the data points. Output 2. Explain in detail a stress value, which quantifies the quality of the embedding. Lower stress indicates a better fit, with distances in the low-dimensional space closely resembling the original distances. Steps. Step 1. Explain in detail. The MDS algorithm first takes the distance matrix as input. Step 2. Explain in detail. It then computes a low-dimensional representation of the data points by finding a configuration that minimizes the difference between the original distances and pay distances in the lower dimensional space. Metrics. Metric 1. Explain in detail. Stress is a common metric used to evaluate the quality of the MDS embedding. It measures the deviation of the distances in the low-dimensional space from the original distances. A lower stress value indicates a better fit. Metric 2. Explain in detail. Kruskal stress is another metric commonly used in MDS. It is a normalized version of stress and is often preferred as it ranges between 0 and 1, making it easier to interpret. Visualization plots. Visualization plot 1. Explain in detail. Scatter plots are frequently used to visualize the low-dimensional embedding obtained by MDS. The coordinates of the data points in the lower dimensional space are plotted on the x and y axes, revealing the relationships and clusters within the data. Visualization plot 2. Explain in detail. Sometimes 3D plots can be used to visualize the embedding in a 3D space, providing additional insight into the data structure. Fine-tune parameters. Parameter 1. Explain in detail n components, the number of dimensions to which the data should be reduced. Parameter 2. Explain in detail dissimilarity, the distance metric used to compute the distance matrix. Possible options include pre-computed if a pre-computed distance matrix is provided, Euclidean distance, Manhattan distance, or other supported metrics. Uncertainty methods. Uncertainty method 1. Explain in detail. MDS, in its standard form, does not directly provide uncertainty measures for the embedding. However, it is possible to use techniques like bootstrapping to assess the variability of the embedding. Uncertainty method 2. Explain in detail. One can also apply methods like kernel density estimation to estimate the density of the data points in the lower dimensional space, giving a visual indication of uncertainty. Challenges and fixes. Challenge 1. Explain in detail. Poor data representation. MDS may fail to accurately represent the data in low-dimensional space if the data has a complex structure that cannot be adequately captured by the reduced dimensionality. Sample use case that resulted in challenge 1. For example, data with nonlinear relationships may not be well represented by a linear MDS embedding. Fixes to challenge 1. Consider using nonlinear dimensionality reduction techniques like T-SNE or ISOMAP. Experiment with different distance metrics that may better capture the data's underlying structure. Challenge 2. Explain in detail computational complexity. MDS can become computationally expensive, especially for large datasets or high-dimensional data. Sample use case that resulted in challenge 2. A very large dataset with many data points may take a long time to process. Fixes to challenge 2. Use efficient MDS algorithms or approximations. Employ dimensionality reduction techniques like PCA to reduce the dimensionality of the data before applying MDS. Consider using parallel or distributed computing to speed up the computations. sklearn, Manifold, Spectral Embedding. Description. Spectral embedding is a nonlinear dimensionality reduction technique that uses the spectrum of a graph Laplacian to embed data in a lower dimensional space while preserving the local neighborhood structure. It's particularly useful for visualizing and analyzing data with nonlinear relationships, where traditional linear methods like PCA might fail. Inputs. X. The input data is a NumPy array of shape n samples. N features. Each row represents a data point, and each column represents a feature. Affinity. The type of affinity matrix to use for constructing the graph Laplacian. Options include nearest neighbors for constructing a graph based on k nearest neighbors. RBF for using a radial basis function kernel. Precomputed for using a precomputed affinity matrix. And more. Outputs. Embedding. The low-dimensional embedding of the data as a NumPy array of shape n samples. N components. Each row represents a data point in the lower dimensional space. Affinity matrix. The affinity matrix used for constructing the graph Laplacian. Steps. Construct the graph Laplacian from the affinity matrix. The graph Laplacian encodes the relationships between data points based on the chosen affinity. Compute the eigenvalues and eigenvectors of the graph Laplacian. The eigenvectors represent the embedding space, and the eigenvalues indicate the importance of each eigenvector. Select the top k eigenvectors where k is the desired embedding dimension. These eigenvectors provide the low-dimensional representation of the data, preserving the local neighborhood structure. Metrics. Reconstruction error measures how well the original data can be reconstructed from the embedding. Neighborhood preservation evaluates how well the embedding maintains the local neighborhood relationships present in the original data. Visualization plots. Scatter plot visualizes the embedded data in the lower dimensional space, revealing clusters, patterns, and relationships. Graph plot displays the graph constructed from the affinity matrix, highlighting the connections between data points. Fine-tune parameters. N components. The desired dimensionality of the embedding space. Affinity. The type of affinity matrix to use, e.g. nearest neighbors. RBF. Gamma controls the width of the Gaussian kernel for the RBF affinity. N neighbors. The number of nearest neighbors to consider for the nearest neighbors affinity. Eigensolver. The method to use for computing the eigenvectors, e.g. RPAC. Log PCG. Uncertainty methods. Out-of-sample embedding for new data points not included in the original training data. You can estimate their embedding based on their affinity to the existing data points. Challenges and fixes. Challenge 1. High dimensionality of the input data. Sample use case when the number of features is very large. Constructing the graph Laplacian can be computationally expensive and prone to noise. Fixes to challenge 1. Perform dimensionality reduction before applying spectral embedding using techniques like PCA or feature selection. Consider using a sparse graph Laplacian to reduce the computational complexity. Challenge 2. Choosing the appropriate affinity function. Sample use case selecting an affinity function that captures the underlying data structure is crucial for effective embedding. Fixes to challenge 2. Experiment with different affinity functions and parameters, e.g., nearest neighbors, RBF, based on the nature of the data and desired results. Consider domain expertise or prior knowledge to guide the choice of affinity function. sklearn, Manifold, TSNE. Description. T-distributed stochastic neighbor embedding TSNE is a nonlinear dimensionality reduction technique. Particularly useful for visualizing high-dimensional data in low-dimensional spaces, often 2D or 3D. It aims to represent data points in a way that preserves the local neighborhood structure of a original data. Inputs. X, a matrix of shape and samples. N, features, where each row represents a data point, and each column represents a feature. Perplexity. This parameter influences the local neighborhood size that TSNE considers. A higher perplexity value leads to larger neighborhoods. Outputs. Y, a matrix of shape and samples. N, components containing the low-dimensional embedding of the input data. Embedding a NumPy array containing the final embedding. Steps. Similarity computation. Calculate pairwise similarity between data points using Gaussian kernel, based on Euclidean distances. Probability distribution. Construct the probability distribution over the data points based on pair similarity scores. This distribution reflects the local neighborhood structure. Low-dimensional embedding. Minimize the Kullback-Leibler KL divergence between pair high-dimensional probability distribution and a corresponding probability distribution in pair low-dimensional space. This is achieved using gradient descent metrics. Kullback-Leibler KL divergence. The KL divergence between the high-dimensional and low-dimensional probability distributions quantifies how well the embedding preserves the local neighborhood structure. Silhouette score. This metric evaluates the quality of the clustering structure present in pair low-dimensional embedding. Visualization plots. Scatter plot. A scatter plot of the low-dimensional embedding, with each point representing a data point. This plot reveals clusters, patterns, and relationships within the data. Pair plot. A matrix of scatter plots showing the pairwise relationships between all dimensions of the low-dimensional embedding. This provides a comprehensive visualization of the data structure. Fine-tune parameters. Perplexity. This parameter influences the local neighborhood size that TSNE considers. A higher perplexity value leads to larger neighborhoods. Experimentation is needed to find the optimal value for the specific dataset. N, components. The number of dimensions in the low-dimensional embedding, often set to 2 or 3 for visualization. Early exaggeration. A parameter controlling the initial exaggeration of the KL divergence. Increasing this value can help find more distinct clusters. Learning rate controls the step size in gradient descent. Uncertainty methods. Bootstrap sampling. Generate multiple embeddings by resampling the data with replacement. The variation between these embeddings can be used to estimate uncertainty. Bayesian TSNE. Extend TSNE with a Bayesian framework to incorporate prior knowledge and quantify uncertainty. Challenges and fixes. Challenge 1: difficulty in finding optimal perplexity. Finding the optimal perplexity value can be challenging, as it depends on the data density and structure. Sample use case: a dataset with widely varying data density may require different perplexity values for different regions. Fixes to challenge 1. Experimentation: try different values of perplexity and assess the results visually. Cross-validation: use cross-validation to evaluate performance across a range of perplexity values. Challenge 2: sensitivity to initialization. The results of TSNE can be sensitive to the random initialization of the low-dimensional embedding. Sample use case: repeating the TSNE embedding with different random seeds can lead to significantly different visualization results. Fixes to challenge 2. Multiple runs: run TSNE multiple times with different random seeds and average the results. Initialization methods: explore different initialization methods, such as PCA or random initialization with specific properties. Challenge 3: computational cost. TSNE can be computationally expensive, especially for large datasets. Sample use case: training TSNE on a dataset with millions of data points can take a significant amount of time and computational resources. Fixes to challenge 3. Approximate TSNE: use approximate algorithms, such as Barnes-Hut T-SNE, which can reduce computational complexity. Dimensionality reduction: pre-process the data with other dimensionality reduction techniques, such as PCA, to reduce the number of features before applying TSNE. sklearn, Manifold, locally linear embedding. Description: locally linear embedding (LLE) is a nonlinear dimensionality reduction technique that seeks to preserve local neighborhood relationships in the lower dimensional embedding. It assumes that each data point can be linearly reconstructed from its neighbors. LLE first finds the local neighborhood for each data point and then computes the weights that linearly reconstruct the point from its neighbors. Finally, it seeks a lower dimensional representation that preserves these local reconstructions as much as possible. Inputs: X. The input data is a NumPy array of shape n samples. N features, where n samples is the number of data points and n features is the number of features. N components: the number of dimensions to reduce the data to. Outputs: Y. The lower dimensional embedding of the data is a NumPy array of shape n samples. N components. Reconstruction error: the reconstruction error for each data point, indicating how well the data can be reconstructed from its neighbors in the lower dimensional space. Steps: find the k nearest neighbors for each data point. Compute the weights that linearly reconstruct each data point from its neighbors. Minimize the reconstruction error in a lower dimensional space by finding the embedding that preserves the local neighborhood relationships as much as possible. Metrics: reconstruction error measures how well the original data can be reconstructed from its neighbors. In the lower dimensional embedding, lower reconstruction error indicates better preservation of local relationships. Visualization plots: scatter plot: visualize the lower dimensional embedding of the data, showing the relationships between data points. Pairwise scatter plot: plot all pairs of dimensions in the lower dimensional embedding to explore potential correlations. Fine-tune parameters: n neighbors: the number of neighbors to consider for each data point. A higher value might capture more global relationships but can lead to overfitting. Reg regularization parameter for the local reconstruction weights. A higher value can prevent overfitting. Eigensolver, the solver to use for computing the eigenvectors of the Laplacian matrix. Auto selects the most efficient solver based on the data size. Method, the method to use for finding the embedding. Standard uses the standard LLE algorithm, while modified uses a modified version that can be faster for larger datasets. Uncertainty methods. Confidence intervals for the embedding estimate the uncertainty in the embedding coordinates by considering the variability in the reconstruction weights. Out of sample extension use a similar algorithm to embed new data points into the existing lower dimensional space. Challenges and fixes. Challenge 1, overfitting to the data. Sample use case when the number of neighbors is too high or the regularization parameter is too low. The algorithm might overfit to the local structure of the data, resulting in poor generalization to unseen data. Fixes. Reduce the number of neighbors. Increase the regularization parameter. Challenge 2, computational complexity for large datasets. Sample use case LLE can be computationally expensive for large datasets, especially when the number of neighbors or the dimensionality of the data is high. Fixes. Use the modified LLE algorithm, which can be faster for larger datasets. Use a smaller number of neighbors. Consider using a different dimensionality reduction technique like T-SNE, which can be more efficient for high-dimensional data. Challenge 3, difficulty in handling data with nonlinear relationships. Sample use case LLE assumes that data points can be linearly reconstructed from their neighbors, which might not hold true for data with complex nonlinear relationships. Fixes. Consider using a different dimensionality reduction technique like T-SNE or ISOMAP, which can handle nonlinear relationships more effectively. Challenge 4, sensitivity to the choice of parameters. Sample use case, the performance of LLE can be sensitive to the choice of parameters like a number of neighbors and the regularization parameter. Fixes. Carefully tune the parameters using cross-validation or other techniques to find the optimal settings for the specific dataset. sklearn, Manifold, Smakeoff. Description. The SMACOF scaling by M-agerizing a complicated function algorithm is a multidimensional scaling MDS technique for finding a low-dimensional representation of data that preserves the pairwise distances between data points as much as possible. Inputs. Distances, a distance matrix representing the pairwise distances between the data points. The input can be a condensed distance matrix, a 1D array with distances between all pairs, or a square distance matrix, a 2D array where distances between points are stored. Metric, a Boolean value indicating whether the input distances are metric true or non-metric false. If metric is true, the algorithm assumes that the distances satisfy the triangle inequality. If metric is false, the algorithm tries to find a representation of the data that minimizes the stress function. N components, the number of dimensions of the embedding space. Init, the initialization method for the embedding. Possible values are random, initialize the embedding with random values. PCA, initialize the embedding using principal component analysis. A ND array, initialize the embedding with a specific ND array. Ninit, the number of different initializations to try. Outputs. Embedding, a 2D array representing the embedding of the data points in the low-dimensional space. Each row corresponds to a data point. Stress, the stress value of the embedding, which is a measure of the goodness of fit. Lower stress values indicate better fits. Steps. Initialization, the algorithm starts by initializing the embedding of the data points in a Low-dimensional space. Iteration. The algorithm then iteratively updates the embedding to minimize the stress function. The stress function measures the difference between the input distances and the distances in A. Embedding space. The algorithm uses a majorization technique to minimize the stress function. Metrics. Stress. The most common metric used to evaluate the quality of the embedding. It measures the difference between the input distances and the distances in the embedding space. Lower stress values indicate better fits. Shepherd diagram. A visualization tool that plots the input distances against the distances in A. Embedding space. Visualization plots. Scatter plot to visualize the embedded data points in the low-dimensional space. Shepherd diagram to visualize the relationship between the input distances and the distances in the embedding space. Fine-tune parameters. N components. The number of dimensions of the embedding space. Increasing the number of dimensions can improve the quality of the embedding but can also make the algorithm more computationally expensive. Limit the number of different initializations to try. Increasing the number of initializations can help to avoid getting stuck in local minima. Metric. This parameter influences how the algorithm interprets the input distances. Setting it to true means the algorithm assumes the distances satisfy the triangle inequality. Challenges and fixes. Challenge 1. Getting stuck in local minima. Sample use case that resulted in challenge 1. If the algorithm is initialized with a poor starting point, it may get stuck in a local minimum and not find the best possible embedding. Fixes to challenge 1. Try different initializations using Ninit. Challenge 2. Long runtime for large datasets. Sample use case that resulted in challenge 2. When processing a very large dataset, the algorithm can take a long time to run. Fixes to challenge 2. You can consider using a dimensionality reduction technique, e.g. PCA, to reduce the dimensionality of the data before applying SMACOF. Uncertainty methods. Bootstrapping. Repeatedly resample the input data with replacement and then fit the SMACOF algorithm to each resampled dataset. Jackknifing. Remove one data point at a time from the dataset and then fit the SMACOF algorithm to the remaining data points. sklearn, Manifold, Spectral Embedding. Description. Spectral embedding is a dimensionality reduction technique that leverages the spectrum of the graph Laplacian to project data points onto a lower dimensional space while preserving the local neighborhood structure. It's particularly well suited for nonlinear datasets where linear methods like PCA fail. Inputs. Affinity. This represents the similarity between data points. It can be provided directly as a matrix or computed based on the data using various methods like nearest neighbors constructs a k-nearest neighbors graph. RBF uses a radial basis function RBF kernel, where the similarity decreases exponentially with distance. Precomputed takes a precomputed similarity matrix. N components, the number of dimensions to reduce the data to. Outputs. Embedding a 2D array containing the embedded data points in the lower dimensional space. Eigenvals. The eigenvalues of the graph Laplacian. These can be useful for analyzing the embedding and understanding the spectral properties of a data. Steps. Constructing the affinity matrix based on the chosen method. A similarity matrix affinity matrix is constructed. It measures the pairwise similarity between data points. Building the graph Laplacian. The graph Laplacian matrix, which captures the connectivity and structure of the data, is derived from the affinity matrix. Eigenvalue decomposition. The graph Laplacian is decomposed into eigenvectors and eigenvalues. Embedding the eigenvectors corresponding to the largest eigenvalues are used to embed the data points in a lower dimensional space. These eigenvectors represent the principal components of the data's spectral representation. Metrics. Reconstruction error measures how well the embedding preserves the original distances between data points. Clustering quality evaluates the performance of clustering algorithms on the embedded data. Visualization plots. Scatter plot visualize the embedded data in the lower dimensional space to identify clusters, outliers, and relationships. Eigenvalue spectrum plot the eigenvalues to understand the distribution of variance and pay. Number of significant components captured by the embedding. Fine-tune parameters. N neighbors for nearest neighbors affinity. The number of nearest neighbors to consider when constructing the graph. Gamma for RBF affinity controls the width of the Gaussian kernel. Random state controls the random number generator for reproducibility. Uncertainty methods. Bootstrap resampling. Repeat the spectral embedding multiple times with different subsets of data points to estimate the variability of the embedding. Sensitivity analysis. Perturb the affinity matrix and analyze the effect on the embedding to identify sensitive regions. Challenges and fixes. Challenge 1. High dimensionality. If the data has a large number of dimensions, it can be computationally challenging to compute the graph Laplacian and perform the eigenvalue decomposition. Sample use case that resulted in challenge 1. Spectral embedding applied to images with millions of pixels. Fixes to challenge 1. Dimensionality reduction. Pre-process the data using techniques like PCA or T-SNE to reduce the dimensionality before applying spectral embedding. Nystrom method. Approximate the graph Laplacian using a subset of data points. Challenge 2. Outliers. Outliers can significantly distort the affinity matrix, leading to an inaccurate embedding. Sample use case that resulted in challenge 2. Spectral embedding applied to financial data with extreme values. Fixes to challenge 2. Outlier detection. Identify and remove or handle outliers before constructing the affinity matrix. Robust affinity measures employ robust similarity measures that are less sensitive to outliers. Sklearn manifold trustworthiness. Description. Explain in detail. Trustworthiness is a metric used to evaluate the quality of a manifold learning embedding. It measures how well the embedding preserves the local neighborhood structure of the original data. A higher trustworthiness score indicates that the embedding is more faithful to the original data's local structure. Inputs. Input 1. Explain in detail the input data represented as a 2D NumPy array where each row represents a data point and each column represents a feature. Input 2. Explain in detail the output embedding of the manifold learning algorithm, also represented as a 2D NumPy array. Each row corresponds to a data point in the input data, and each column represents a dimension in the embedding space. Outputs. Output 1. Explain in detail a single numerical value representing the trustworthiness score of the embedding. The score ranges from 0 to 1, with 1 indicating perfect preservation of the local neighborhood structure. Steps. Step 1. Explain in detail for each data point in the original data. Find its k nearest neighbors KNN based on the original data's distance metric. Step 2. Explain in detail for each data point in the embedding space. Find its k nearest neighbors KNN based on the embedding space's distance metric. Step 3. Explain in detail. Compare the KNN sets in the original space and the embedding space. A higher trustworthiness score indicates a greater overlap between these KNN sets. Metrics. Metric 1. Explain in detail. Trustworthiness is itself a metric used to assess the quality of pay. Embedding. Metric 2. Explain in detail. Other metrics such as continuity, stress, correlation can also be used to evaluate the quality of the embedding. Visualization plots. Visualization plot 1. Explain in detail. Scatter plots can visualize the original data and pay. Embedding to visually inspect the preservation of local structures. Visualization plot 2. Explain in detail. Heat maps can be used to show the trustworthiness scores for different values of K. The number of nearest neighbors. Fine-tune parameters. Parameter 1. Explain in detail. K. The number of nearest neighbors considered when calculating trustworthiness. Parameter 2. Explain in detail. N neighbors. The number of nearest neighbors used in the manifold learning algorithm. This parameter influences the local neighborhood structure and can impact trustworthiness. Uncertainty methods. Uncertainty method 1. Explain in detail. Bootstrapping. Repeatedly resample the data with replacement and calculate trustworthiness on each resampled dataset. The variability in trustworthiness scores across these samples can be used to assess uncertainty. Uncertainty method 2. Explain in detail. Cross-validation. Split the data into folds and calculate trustworthiness on each fold. The variance in trustworthiness scores across folds can be used to estimate uncertainty. Challenges and fixes. Challenge 1. Explain in detail. High dimensionality trustworthiness may be sensitive to the curse of dimensionality, where distances between data points become less meaningful in high-dimensional spaces. This can lead to unreliable or inaccurate trustworthiness scores. When working with image data with a large number of pixels, the trustworthiness score may be inaccurate due to the high dimensionality. Dimensionality reduction techniques. Apply dimensionality reduction techniques like PCA, TSNA, or UMAP to reduce the dimensionality of the data before calculating trustworthiness. This can mitigate the impact of high dimensionality and improve the accuracy of the score. Challenge 2. Explain in detail. Nonlinear data trustworthiness may not be effective in evaluating the quality of embeddings for highly nonlinear data. The linear assumption underlying trustworthiness might not accurately capture the underlying structure of the data. When using manifold learning to embed data with complex nonlinear relationships, the trustworthiness score may not accurately reflect the quality of the embedding. Consider alternative metrics for highly nonlinear data. Consider using other metrics like continuity, stress, or correlation to evaluate the quality of the embedding. These metrics may be better suited to capturing nonlinear relationships.